Thank you, Norm. Good morning, good afternoon, good evening, wherever you are. Welcome to our webinar. Today, we'll start the webinar by, of course, introducing our CEO, Mr. Dan McLean, to provide his opening remarks. Dan, please.
Thank you, Matt. And hello to everyone. Thank you for taking the time to join us. This, I think, is about our seventh webinar since all of this COVID stuff happened. And it is my hope that everyone is staying safe during these very challenging and difficult times. A lot of us are moving back into the office or back into the classroom, and that's a great sign. But we found over the last 18 months that this webinar platform is a great way to get our message out to a lot of people. And I hope that we can continue to do this over the next 12 to 18 months and even going forward. So let me just start by saying, you know, the PTRC, we've been for 23 years been ahead of the curve on a lot of research around CCS and CCUS, in particular as it pertains to CO2 storage. But at the same time, we have invested in research in other things, AI in particular. And this is our second webinar on this AI machine learning methodology. The first one had the U of R, some folks here were there, and some folks from the Saskatchewan Research Council. Both organizations are making great headways to understand and apply this technology. I'm really excited about today because you're going to see an application of AI in a world that I'm quite familiar with. I've been in the oil and gas game for well over 40 years. I'm what I call a classically trained reservoir simulation engineer. I've worked for years with geologists, geophysicists, petrophysicists around the world, modeling reservoirs from the Western Canada Sedimentary Basin to offshore West Australia, offshore West Africa, and in the Middle East. And I can tell you, it's a very complex process to work with these folks to understand the geologic architecture, building history matched models to understand the resource risk that we're dealing with and to make better decisions, capital decisions going forward. I look at the state of the situation today, and you can appreciate that there is a strong movement to move away from fossil fuels. That's fine. Moving into renewables, that's great too. But this energy form is going to be around for a long time. But unfortunately, we don't seem to be attracting a lot of folks, geologists, engineers, into this discipline. So when I project 10 years into the future, are we going to have those skill sets available to do this kind of classical reservoir simulation? I don't know. I don't think so. So what we're going to talk about today has applicability into the future. Think about what we're doing today. The engineers and geologists of today are used to using a lot of data. And this is what this is all about, using data. Now it's about using it smartly and about understanding what this is telling you. A long time ago, someone told me, they said, you know, the reservoir is talking to you. Are you listening? Today, you're going to be able to see how we are listening to the reservoir and how we are going to take that and convert it into a language that we fully understand and feel confident that we can use it to make good business decisions going forward. So think about that, listen to that, and I'd be really curious to see how you see this. I hope you see it in the same way that I do, that this may be another way to better understand the resource risk going forward into the future. So with that, I'm going to turn it back over to Matt, and you can start with your introductions.
Great, thanks very much, Dan. And as you said, that it's all about sustainable energy production and management. You know, every improvement we make in the process of energy production to make it more efficient is very important in ensuring the sustainable development of our energy resources, taking advantage of super computational capabilities that are available to us today, and making artificial intelligence and machine learning useful in energy production is certainly an important step in the right direction. So today's webinar, as you all know, using machine learning for oil production prediction, sensitivity analysis, history matching, and optimization. This work is a collaboration between software systems engineering and petroleum systems engineering at the University of Regina. Our speaker today is Dr. Mohamed El-Darieby. He is a professor in software engineering at the Faculty of Engineering, University of Regina. He has more than 25 years of experience in software engineering. He led more than 20 competitive research and consulting projects funded on a provincial, national, and international levels. Dr. El-Darieby has more than 60 publications in technical conferences and journals, in addition to numerous technology transfer reports. He holds a PhD in systems and computer engineering from Carleton University in Ottawa, Canada. His research collaborators, Dr. Ezeddin Shirif, who is a professor of petroleum system engineering at the University of Regina. Dr. Shirif, unfortunately, due to an emergency, could not join us today. PhD students who also collaborated and worked hard on this project are George Dawood, who, as I said, is a PhD candidate at software system engineering. Arifur Rahman, who is a PhD candidate at the petroleum systems engineering at the University of Regina. And Mohamed Ahmed, who is also a PhD candidate at the Faculty of Engineering in Electrical Systems Engineering. Without any further ado, I ask you, Mohamed, to please start your presentation.
Well, good morning, everyone. For those who are in Western Canada, and today we're going to be talking about a presentation on our topic, where we studied machine learning and its applicability to reservoir simulation. I would invite my co-presenters, George and Arif, to jump in at any minute and make any comments that I miss, or if they have other remarks on the slides. And today we're going to divide the presentation roughly into two parts. The first part is a general overview and a scope and objectives, and some description, high-level description, and then the second part would be a presentation with experimental details and results. You would have opportunity to ask questions after each part. We thought that this idea of dividing into two parts would help chunk the amount of information and set the expectations for everybody, and hopefully serve as many audience as possible. The objective of the research and of the presentation today was to explore the applicability of deep neural network, deep machine learning in reservoir simulation. And we divided this objective into the three objectives that you see here on this three-dimensional graph. So we studied a number of simulation processes listed here, those four of them. And we're going to show you these the results behind these studies. We also tried to study the different capabilities of deep neural network and how they can be programmed, how they can be built and used in simulation processes. And we studied all of this in terms of the accuracy of the characterization and prediction of the reservoirs, as well as the computational speed and cost of the deep neural network in carrying out these informations. For me to start, I would like to start with this slide where it differentiates between artificial intelligence, machine learning, and deep learning. And generally speaking, Deep learning is a supervised way of artificial intelligence. Generally speaking, engineers and data scientists would prepare a number of data sets and scenarios, feed them into the deep learning network, and get results out of that. But the majority of the work, like this is at a usage phase, the majority of the work is actually done training those deep neural networks to be able to predict accurately and correctly and in a faster way the results that we would like to achieve out of the model. The first step we wanted to start with, please know that this is a project where we had a very steep learning curve. I'm from software. Dr. Shirif was from petroleum. For us to speak the same language, we had to go through this very steep learning curve, and for our collaborators as well. But we started with a simplistic scenario here, or actually 3 different scenarios to explore the different architectures of machine learning and deep neural network. And I list 4 of them here that we've used in this project. We tried to work with them, as you can see in this figure, as a black box that we program. And I'm going to show you in the next slide what's inside this black box. But we basically fed the neural network with some data about a reservoir, and then we got some prediction for the output out of that neural network. We compared the output to the results of the CMG simulator, and we noted that the prediction was really good. The accuracy was very high, and the speed of calculation was very fast. We repeated this for different architectures. We programmed the architectures, we trained the architectures, and we spent a lot of time trying to get the box to work and to produce the accurate results. And this gave us a lot of confidence on the first step and pushed us to go into the next step. In the orange box that we're seeing, the deep neural network, this is how it looks like from the inside. The one to the left, the upper left figure, is actually a deep neural network. And you would define that with a number of hidden layers in between the input and output layers. Those are basically the circles in the middle, are arranged vertically in what is known as layers. Deep would have a few of these layers, and there has to be some sort of an expertise there on how to set up the layers, the number of layers, and the number of nodes in one layer. It's not that simple that you just add as many of those and you will get a more accurate result. Actually, the less number of layers or the more number of layers would be bad and would not achieve results. You have to really optimize the architecture. But then each one of them is an orange box. You provide the input and it predicts the output, and through the training it actually fine-tunes the output to the accuracy required. And for us to be able to predict over a long period of time, then we use the figure to the right bottom part in the picture, the one that I say architecture on. And the idea here is to be able to use this in a time series type of architecture to be able to predict the performance of the reservoir over a number of time units, and you can really recursively repeat this as much as you want. And we've, again, the first objective for us was to attempt this with different architecture and test their performance and test their accuracy and see which one is the best for us. And then this took us to the next phase of experimentation, where we started adding a space dimension. So the first phase, we had some prediction, architectures, and time dimension. And in this second phase, we started adding space dimension to the neural network capabilities. We divided a reservoir into hundreds of grids, and those grids are smaller blocks that are physically adjacent to each other. And we tried to use the neural network to quantify the pressure distribution and the saturation at each grid block for different scenarios of homogeneous or heterogeneous reservoir using radial or Cartesian coordinates. And as you can see there from the figure, the neural network there as well has those inputs. and those outputs. The inputs are basically the saturation and pressure of different grid blocks at a particular minute in time, and the prediction would be the pressure and saturation at the next minute in time. Or also, the inputs would include the saturation and pressure of adjacent reservoir to the one that we're calculating these pressure and saturation for. So we basically here take the input from the previous time units, as well as from the adjacent grid blocks to calculate the pressure and saturation for the block at the next time in time unit. And we were able to achieve this, and we like the results very much, and it really helped us with a number of other things. But then we moved on to also analyze how we can use the neural network to study the effect of the different parameters of inputs on the output. And for that, we carried some sensitivity analysis experiments, and we used the two main sensitivity analysis methods, the local and global. The local, as maybe most of you know already, considers the effect of only one input parameter on the different outputs that we have, as we can see here in the figure to the left. But also this might, although yeah, this is very important, it tells us how the output is affected by each input parameter. The combination of input parameter is also very important, and this is why we tried to get the global sensitivity analysis and study it, and we used two of the very common methods for global sensitivity analysis. Again, we were really happy with the results that we got and the speed and accuracy of the neural network. We took this to the next phase where we grouped the previous building blocks, the prediction, the flow analysis on a grid block level, and the sensitivity analysis, and tried to feed it into a history matching sequence like the one we're presenting here for you. And the idea here as well was to understand the applicability of deep neural network into history matching, but also to try to use other AI technique. In this particular case, we use genetic algorithms, which is a very well-known search algorithm that help optimize many of the engineering processes. And obviously here, because of the non-uniqueness issue of the history matching, the genetic algorithm was really helpful in reducing the number of scenarios that we would be running. And using a fast neural network as well would really help reduce the thousands of iterations that typically a petroleum engineer would use for history matching into a very limited number. And I think we were very successful with that as well. Finally, all of this led to us work with the genetic algorithms and the neural network, and help us try to understand different production profiles, and help us come up with different plans for production profiles. In particular, in this graph here, we use the genetic algorithm to calculate for us different time duration of injection of water and gas at different distributions. And we use the CMG simulator to also help us with generating some of the data here. And ultimately, the produced results are optimized for different durations and different injection rates. And in our opinion, this really helps with providing petroleum engineers with a lot of options and possibly the results of those different plans. And hopefully this would result in optimized operation and optimized production of the well. To summarize, we basically, again, considered a number of different simulation reservoir procedures. We use them in this sequence that I show here in the figure. And while we're doing this, we were adding or building up our investigation of the capabilities of the neural network, building up the code that we write, building up the features that we add to our neural network libraries. And ultimately, we were happy with getting results that are very accurate, with relative error less than 1% when compared to the results that you would get from the CMG simulator. But maybe we had a much faster performance. And we think really this is going to be way more cost effective when it's taken to real world with real reservoirs and with real data set. I think this summarizes what I wanted to say. Again, we started with the neural network architecture. We investigated all of them. Then we added the time and space dimension. Then we had a study of the input factors, single and multiple factors and their impact on the output. And then we integrated neural network with other AI techniques to help with optimize and reduce the number of scenarios in a non-unique situation. I think this sort of quickly gives an overview of what we wanted to say. I would stop here for a few minutes and entertain a couple of questions before we get into the more detailed presentation with more scenarios and more results.
Okay, thank you very much, Mohamed. We are open to questions if there are any.
And as I said, you can use the Q&A box at the bottom to type in your question. You can also send it via chat, although that can be a little more of an issue, but that's all right. It will go to all the panelists if you use the chat. So Q&A or chat. And as I said, we prefer Q&A because we can then keep track of it on an Excel sheet for later. Okay, first question. Is your model applicable to a wide range of reservoirs?
Yes, and we need to adapt the model to the specifics of the reservoir. So the knowledge that we built is absolutely applicable. We need to, however, make some modifications because each reservoir is different.
Great, thank you. Okay, I see no other questions at the moment. Oh, here's one. Wait a sec. What platform or software did you use for NN?
We use PyTorch mostly. We also, in some parts, we use MATLAB to do some other aspects, but generally speaking, the output, we sort of consolidated it into PyTorch, Python Torch. I hope you're familiar with that. It's sort of the industry standard or one of the standards right now for developing of the neural network.
Great. And there was another one that's come in. Has this been tried in thermal reservoirs?
Okay, thank you so much, Adrienne. No, we have not.
Okay. Do you have a good rule for the number of training sets to be accurate in the test set?
Unfortunately, no. This is an active area of research right now. There are methods, though, that can help you optimize those things.
Okay.
We wouldn't have a specific rule, or life would have been extremely much more simpler.
Good.
Okay, we really believe that PyTorch, this is the next question. Please go ahead, Norm. I'm sorry, yeah.
No, that's right. The next question, please answer why PyTorch and not, I don't know how to pronounce that, scikit-learn.
Scikit-learn. We really believe that PyTorch is much more powerful, and we loved it. We used also MATLAB. The number of tools there are great. We just preferred PyTorch, I guess.
Yeah.
It's also way more compatible with the Google new cloud computing architecture, where you can use the GPU and TPUs, and that would really help a lot with the performance of the neural network and the speed of computation. The next question is from my colleague, Christine Chan. Did you compare the performance of different DNNs? Yes, we did, Christine. Between RNN and LSTM, yes, we did. We generally prefer to use LSTM in this situation. Again, in other particular situations, maybe RNN would be better, but we preferred LSTM.
Especially for this question, especially for the homogeneous reservoir, we prefer the LSTM method, and it predicts very well the performance of the reservoir. And for the heterogeneous reservoir, we usually use the GRU method.
Okay, the next question is from my dear colleague, Gary Zhao as well. if different reservoir simulators are used, how will they affect the outcomes? I think, Gary, what you're saying here is different simulators. Do you mean different neural networks? Yes, if you mean so, different neural network architecture would make a difference in the speed and accuracy of the outcome. And this is part of what we have tried to explore. We were trying to explore the different architecture, the different parameters, and how they would affect the outcomes in terms of accuracy and in terms of speed. I hope this answers the question, Gary, if I understand it well. Now, the following question is from my colleague, Christine Chan. Thank you, Christine. How big are the data sets for the training? Arif and George, can you help me out with this one?
18, we usually use the 5-year project. That means the 1800 days. We use the 1800 days data set for the training. So each day we use the data set for 1800 days.
The next
100 of grade blocks per day, so it's a huge number. It's more than 32 gigabytes.
Yeah.
The next question is from our colleague Adrian. Will you be talking about the network architecture optimization algorithms, etc.? Yes, we're going to be providing some further details down the road or in the coming few minutes as well, Adrian. Please, if you can listen to those, and then if you have further questions, we can provide further details. The next question is from Mr. Abdullah Al-Gaufi. The model requires previous time step for space and time parameters. So does it work with green field predictions? Arif?
Yeah, it will work for any field, but before we use that architecture, we have to train our model for that specific reservoir. So once we have different kind of reservoirs, so we have to train our model first with that reservoir parameters, then it will definitely work for that reservoir.
The next question is from Mr. Jalal Jalili. Any comments on using MLPs versus CNNs? We did use CNN as well, Mr. Jalal. MLP is multilinear processors. Is that right, George? What is MLP, Mr. Jalal? We did use CNN for the space dimension, and we were able to optimize them as well to achieve better performance. Now, I think what you mean by the linear processors is that MLP means. No, we did not really consider it, if I understand it right. If you can type in what do you mean by MLP, then that would be great.
Okay.
The last question is from Mr. Adrian as well. I'm in business admin, so could you explain the target variable in more lay terms? I guess the target variable is basically how much oil do we produce out of the oil reservoir? How much oil do we get versus how much water or gas do we get? And we control the amount of injection of oil and gas so that we achieve the most oil out of the reservoir. But we also have to consider the static parameters, the physical parameter and seismic parameters of the reservoir. So those are sort of the parameters that we use. And the output is basically how much oil we get, and that would be ultimately turned into a dollar figure, I guess.
Okay, so let's just have these last two. The anonymous attendee, I'll leave your, the two or three that have just come in. We're going to have more presentations here, or more of the presentation. So we'll have the next two, Jalal and Abdullah, answered, and then we'll save the other two. I'll leave them up for the beginning of the Q&A after your last part of your presentation, Mohammed.
Yeah, so Mr. Jalal, thank you for explaining this. Yes, the multi-layer perceptron, the usual feed-forward network, we use this in the very first step, and we understand it very well. It doesn't have a space dimension, though. The CNN can process the space dimension, and this helps us a lot when we divide the reservoir into the smaller blocks. I really don't think the multi-layer perceptron would work there well, and we haven't obviously tested it because we know it will not be. If you are interested in the space dimension, I guess one of the things that you can try is the CNN, and maybe put a lower priority to the MLPs. The last question from Mr. Abdullah. Have you thought of considering physics-based DNN to verify the results of the black box type of regressor?
Actually, can I answer this one?
Sure.
Actually, in the numerical reservoir simulator, we considered the physics behind it. But for the beauty of machine learning is, for machine learning, we did not consider the physics behind it. We make a relationship out of the data. The data we provided to the open computer algorithm, that data is learned by the computer and we get our output. That means that machine learning techniques does not consider the physics behind it, but it can make a relationship between input and output parameters. I think, I hope I answered the questions.
Yeah, and
Okay,
Norm, if you allow me, I guess this also relates to the very last question of Mr. Shivanand Solomon. The laws of physics are embedded in the neural network, and that's why we do the training. So if you have a very large data set you use for the training, the neural network itself gets the laws of physics embedded in the neural network, and this helps us predict the output.
okay, good. Okay, let's continue with your presentations, Mohammed. I'll leave these up, these two that are still there, and
Sure.
And we will get to them. Okay.
Okay. Now we're gonna.
You're muted.
Oh, was I muted? Oh, okay. Now, again, this is the second part of the presentation, and I would like to remind you that these were the research objectives: investigate a number of simulation processes, investigate different DNN capabilities and build those, and then investigate the accuracy of the predictions and the computational speed of the reservoir. Now, I would like to invite Arif and George to start talking to us a little bit about the results and simulations and of what we've done.
Okay. Okay. So as we mentioned earlier, that in numerical reservoir simulation, literally, we tell the computer what to do and how to act. However, you tell the computer what to do and how to act in incredible detail. You tell, multiply this with that, calculate this, so on and so forth. But the computer does not do it by yourself. You just tell it what to do. In machine learning, we use multiple open algorithms to do our task. The same algorithm can be used for multiple problem solving. The computer algorithm is open to do its task and learn it from the data you provide. Now, here we, in order to predict the future. George, can you?
Yeah.
Okay. Yeah. In order to predict the future, it is very important to predict the future behavior. That means how the reservoir will act in future. We need to know the behavior of the reservoir. That's why we develop our proxy model to investigate the important feature of the reservoir and how the reservoir behave in the future. Here we use artificial neural network, LSTM, GRU, and RNN to develop our proxy model. These analyses will help us to decide which neural network will provide us the best match and how we can improve the chosen machine learning technique. At the end, our developed model will assist us in quantifying if there is any uncertainty associated with our model. We start our analysis with very simple case, for example, the homogeneous reservoir with single well, and then we move forward to the complicated reservoir, that means the heterogeneous reservoir and the multi-well reservoir. Now, the result of this analysis will be discussed by my colleague, George.
Thank you, Arif. For the first problem, which is production prediction, our goal is to forecast the production of a reservoir according to a previous history. So we get our data from an numerical simulator and divided into two parts. The first is the history, which is used to train the model so that the model can capture the pattern of the production. And then this model will be applied to predict and forecast the production in the future and compare this with the value provided by the second part of the data, which is the validation part. We tried 4 architectures for neural network, which is, sorry, present here.
Yeah.
Okay, which is, okay. We tried 4 neural network architecture, which is feed-forward neural network, RNN, LSTM, and GRU. Each of them are trained according to the previous data and validated using 3 metrics, which is mean absolute percentage error and mean absolute error and R squared, and also compared in their computational time. And for the first scenario, which is a homogeneous reservoir with 1 production well, we find that LSTM and GRU provide us with the highest prediction accuracy, but GRU gives us the result in a faster way because it is more similar than LSTM. Next slide, please.
Yeah, for the colleague who asked, you can consider the NN here as the feed-forward network or the MLP that you referred to.
Okay, for a more complicated scenario, we starting with a homogeneous reservoir with 1 production well as the case before, but we added a 4 injection well. This add a lot of complexity to the model, and also we tried to do our prediction using the 4 architecture and found also that LSTM and GRU provide us with the best values. Next slide. The last one in the production prediction, we try for a heterogeneous one. We wanted to ensure that our models, our proposed models, can work with complicated reservoir as heterogeneous reservoir with a single well. And as you can see in the figures, that is the validation values for the water produced, the oil produced, and gas produced from this reservoir in this case, and also the values of LSTM and GRU are the best, and GRU has the least computational time, then LSTM has lower than LSTM. So in real data, we propose that using LSTM or GRU according to the computational time constraint needed.
And you would notice from these 3 different scenarios that, again, we're building up the capabilities in terms of the code, in terms of optimizing the neural network, the architecture, and in terms of comparing the different 4 architectures that we've listed here and understanding how they operate and understanding their performance and obviously their accuracy.
Now, as we know that after the primary production, it is very important to know how much fluid is there remaining in the reservoir and its location to perform the secondary and tertiary recovery technique. One of the main purposes of performing the fluid flow analysis is to locate and quantify the remaining well pools in the reservoir. Here we use the RNN to find out the well saturation and pressure distribution of each grid block with time. We take the previous time step saturation and pressure values to find out the grid pressure and saturation with time t. These analyses will help us to find out the remaining well in the reservoir at which location, and that will help us to make a decision to where to drill new wells for the production optimization. So for our cases, we use first the most simple homogeneous radial reservoir by ignoring the relative permeability. Then we use the reservoir with considering the relative permeability effect to perform our analysis. Then we move to the heterogeneous reservoir. Now the results of the fluid flow analysis will be discussed by my colleague George.
As you can see in the figures below, as a reservoir is divided into grade blocks, and for each grade blocks there are 4 quantities to be calculated, which is oil saturation, gas saturation, water saturation, and the pressure in this block. And to predict this value, as Arif has described it to you, we are using 2 information. Is the time information, because we are using the data of the previous day of this block, and the spatial information, because we are using the surrounding blocks to calculate this value. We tried the radial model, which is shown at the left, and the Cartesian model, which is shown at the right, and provide models, neural network model for both of them. Here is the first scenario in fluid flow analysis. We are trained a model to predict the 4 quantities for a homogeneous radial reservoir by neglecting first the relative permeabilities and comparing the values with the numeric simulator values from CMG. This works in 2 modes. The first is 1-day prediction mode, which you are using the previous day to predict the coming day values for each block in the reservoir. And the second is a successive prediction mode, in which the prediction is done successfully from the first day until the end of the production. This adds a more complexity to the model, because we have a risk of error accumulation here, but the result was good. The figures you can see here is 2000-day successive prediction, which means that we start only with the data of the first day and predict the second day, and use the prediction of the second day to predict the third day, and so on until the end of 2000 days. And here is the results of our model compared with a numerical simulator, which is CMG simulator. Here is a summarizing of our results. The figure here shows how the mean absolute percentage error it changes with time in a successive prediction way, and the table shows the one prediction error results. And as you can see, the results is good for both modes. Next slide. Here, petroleum guys have told us that we have to consider what is called relative permeabilities, which is something hard for us to understand. But after we are introducing it to the model, because we want our model to be more general, not to work in a specific case, the result is good. As you can see, here is after 2000 days of successive prediction. The 4 predicted quantitative changed as the are drawn versus the radius from the well, and compared with the CMG values, and the result is nearly the same. And here's summarizing of the successive prediction accuracy or the error, and 1-day prediction error. Next slide. Then we goes to as a Cartesian reservoir. For Cartesian reservoir, for single well, single layer, homogeneous reservoir with the simplest scenario, we try to we are proposed a model that can predict the pressure as a fluid saturation and each grade block. If you can see the figure here, each pixel, each dot in this image represent a grade block. With color, the color maps to a value, and this map can be shown using the color map bar beside the figure. Our model is trained to predict the values for each block in this reservoir in the 2 modes, the 1-day prediction mode and in a successive prediction mode. You can see in the first row from left to right, that is the value of CMG at day 1000, and the second column is the predicted value by our model, and the third column is the relative error at each grid block between the two results. The first row is for pressure, and the second for oil saturation at each grid block. And the result is good, is less than 0.5%. And here is summarizing our results in success prediction mode in the first figure, and in 1D prediction mode in the table. Next slide, please. Then the last scenario in fluid flow analysis was a heterogeneous reservoir. And for heterogeneous reservoir, we have to add the surrounding blocks, because all of this are cooperating to calculate the value of the current block we wanted to calculate. So we use convolution neural network, and as you can see in the figure in the left, for using convolution neural network or convolution neural layer, the surrounding blocks are cooperating together to determine the value of each block in the output. We proposed a model, a deep neural network model with convolution neural network, and apply it to heterogeneous reservoir. Next slide, please. And here's the result for this. Again, this is after 2000 day successive prediction, starting only with day 0, that is the only data given, and you compare it after 2000 successive prediction, the result from CMG simulator with the result of our model. And here is in the first row, this is the pressure, and the second row is the oil saturation. And as you can see, the error is less than 0.1%. And here is a summary of the successive prediction error changed with day for this heterogeneous reservoir in the figure, and in the table you can see 1 day prediction errors. And as you can see, the result is good, and we are moving from each scenario to another into a general model that can be used to replace a simulator in future.
Yes, George, and I guess from this set of scenarios, I hope you got the message that we added the analysis over the time and the space dimension of the reservoir production process.
Now, the sensitivity analysis. In order to predict the future behavior of a reservoir, there are many parameters that have to be considered and tuned. Therefore, knowing which parameter has the most impact on the production value is an important task. Now, finding the relative contribution of design parameters such as permeability, porosity, bottom hole flowing pressure, fluid compressibility, fracture half length, compressibility in a variability of a given performance in a heterogeneous and multi-phase petroleum reservoir is a critical step for the optimal design and control of well recovery processes. After completing the sensitivity analysis, we will be able to answer some of the following questions. What are the major impacts? That means the model outcome versus the input variables. What are the key effects? What is the best way to prioritize a collection of input variables based on their contribution to output variability? Which input variables should be chosen if we could reduce the uncertainty of one or more of them? When and how do parameters interact among themselves? If more samples become available, what are the primary reasons of interest in the parameter space? And finally, does the model mimic well-known behavior of the process of interest? Now, in order to answer all of those questions, we perform the sensitivity analysis using the machine learning approach to find out the most effective parameters of a particular process, whether it is a water flooding, gas flooding, steam flooding, or CSI. We conduct both local and global sensitivity analysis. In local sensitivity analysis, only one particular parameter is chosen to investigate the effect its effect on output, which is well recovery factor or well production for our case. But for most petroleum researchers are interested in global sensitivity analysis, as it will consider all input parameters and also their interactions among themselves. In our study, we usually use Sobel and Morris analysis to find out the most effective input parameters. Now the result will be discussed by George. Next slide.
Thanks, Arif. A previous slide, please. As you can see in the equation, this is the equation of the first method of sensitivity analysis, which is Sobel method. In this method, we are using the function f, and we wanted to find the most important parameters for this function that affects it a lot, which is x here. This is done traditionally using a numerical simulator, which takes a lot of time for each run, and it will have 1,000 of run because this is measured in Monte Carlo simulation-like method, which is called Sobel sensitivity analysis. And to reduce this time, we are replacing this function from a numerical simulator to our neural network. The neural network will simulate the reservoir instead of the simulator. And to do this, it have to be trained with just hundreds of runs, which saves a lot of time because the Sobel analysis itself takes thousands of runs. So making this work on the neural network saves time than making it working on a numerical simulator. Next slide. Here is the result we got, which shows us the mean effect for each parameter, for each of the input parameter over the output of the average pressure, oil production, and gas production. As the values is compared and validated with the numerical values given by CMG. It has the same trend, not exactly the same value because of the random nature of this process, which means that it is different from a run to another, but has the same trend as produced by the numerical simulator. Next slide. Here is a second method, which is Morris sensitivity analysis. It is a much similar method. It looks like Sobel, but it's similar than it. And we use the same trend model for this method. Just it provides us with two information, which is the mean and the standard deviation. And according to this mean and the standard deviation, the input parameter can be categorized into 4 classes, which shows the impact it is low or high, linear or non-linear, as shown in the figure below. Next slide. And here is the result shown to us for average pressure and the cumulative oil production and the gas production using Morris sensitivity analysis.
Now, the history matching. The act of adjusting the developed model with real reservoir production data is called the history matching. History matching is capable of improving and validating the reservoir model based on the iterative process. This approach analyzes the reservoir parameters and get informed from the data set. Then it incorporates the reservoir characteristics with the observed data to tune and train the simulated model. After performing this process, the model will be ready to predict the production data for the studied reservoir. In order to perform history matching, we used our developed proxy model. We insert input parameters into our model and the existing field production data into the model. If it closely matches with our model, then we can say production history is matched and we can perform the future production prediction. But if it does not match with the field production, then we have to tune our input parameter until it matches with the field production. The main advantage of history matching is its ability to predict the future data based on the previous historical data with a high level of reliability and the minimum amount of time. The accuracy of history matching depends on the quality of the proxy model and quality and quantity of the pressure and production data. Once a model has been history matched, it can be used to simulate future reservoir behavior with a higher degree of confidence and accuracy. Next.
Sorry, previous slide. As you can see here, there is a genetic algorithm is applied to search for the input parameters that matches the real field data. And for that, the genetic algorithm will run the simulator and compare the result of the simulator with the real data for the previous history of this data. And it changes the input and search for the input that provides the match. To reduce this, we are using the static parameters suggested to us by sensitivity analysis. We run it in a small scenario, which we are just wanting to find two values: the porosity for the blocks of the reservoir, and the PHP, the bottom hole pressure for the reservoir. This is as a result, as shown in the table, it is nearly the same as CMG, and also the benefit here is running this model over the simulator takes a lot of time, but running it over the neural network model is much faster. Next slide, please.
Yeah. One of the ultimate goal of this study is to use the genetic algorithm to optimize the well production. From the outcome of the fluid flow analysis, we will be able to quantify how much fluid is there remaining in the reservoir. And in order to optimize the production, we know where to drill the new wells, production or injection wells, or we have to drill new infill wells between them. In addition to this, we also know which input parameters needs to be optimized to increase the production from the fluid flow analysis. For example, in a tight well reservoir, we know that we need to fracture the reservoir, and what will be the fracture half length and where will be the location of the horizontal well will be decided by the fluid flow analysis. So in this study, we use 1 production and 4 injection well to optimize the field production using the genetic algorithm. First, we use the primary production, then we inject the, then we do the water flooding followed by the water alternating gas flooding to optimize the production. In our study, we use the genetic algorithm to optimize the well production. George.
As I've tell you that we are optimizing the production profile, which is the 5 periods T1, T2, T3, T4, and T5, in which there are alternating between production and water injection, then another production, then production and gas injections, then another production. The goal here is to maximize the produced oil and to minimize the produced water and gas. What we are controlling is the 5 periods and the maximum bottom hole pressure for injected water and injected gas. So we trained a neural network model shown below, and this neural network model will take these 7 inputs and produce 3 outputs, which is cumulative oil production and gas production and water production. And then this will apply to a genetic algorithm to maximize an objective function. And the objective function will be that we wanted to increase the oil production, but because of economic aspects, there is a penalty of water produced and gas produced. And this penalty is provided by minus alpha and minus beta here, with alpha and beta at constant, as they are subscribed to simulate a penalty of water producing and gas producing. And this alpha and beta should be produced by economic studies. And here is the result. As you can see, we run this model upon 12 values of alpha and betas, and these values and the objective function is maximized and provide us with 12 production profile. And this profile then is produced is introduced to CMG, and here is the result of CMG.
Just to interrupt you quickly, it's already 11 o'clock, but it's okay. We're going to continue for another few minutes, and then we'll try to entertain a couple of questions also, maybe add another 5 to 10 minutes. Thank you. Go ahead, guys, please.
Okay, so to conclude, again, we tried to investigate the applicability of the deep neural networks to the different procedures of simulation that we spoke to you about: the production prediction, the fluid flow analysis, the sensitivity analysis, the history matching, and the optimization. We tried to build our libraries of neural network and build their capabilities in terms of code, in terms of abilities, and in terms of configuration and architecting the neural networks. We're generally very, very happy with the results we've achieved in terms of accuracy and speed. We really believe that this is going to enable us to continue the work and delve into further details of these procedures. And this is some examples of the future work that we're intending to work on, specifically when we're considered the CSI, the cyclic solvent injection, and the capabilities of the neural network to model CO2 storage and optimization, and even analyze the risk behind leakage of CO2 from cab rocks. We really are confident that we can use these deep neural network to model these simulations in an accurate, fast, and more cost-effective way. And I think we're done by this. We're sorry that we took a couple of minutes over the time. We would be entertaining a few more questions, please.
So there are two remaining questions, Mohamed and others.
Yes.
You want to go ahead? Yeah.
So training your model using reservoir simulation output, doesn't that defeat the purpose? No, we basically did train the model with a simulation from the CMG, and we compared our neural network to the CMG. So the whole purpose here was to investigate or compare our neural network to the CMG in terms of accuracy, performance, and sort of cost effectiveness. And we really believe that this was a good progress that we made. Please note also that the simulator, the CMG, providing us with some data provides us with a lot of flexibility, because the number of scenarios that we were designing, we would have looked for a number of data sets that would achieve or would help us study these scenarios. And this wouldn't have been really that possible in a one-year project. So what we've done, I think, is decent enough for the purposes of this experiment for 1 year. Arif and George, any other comments? Okay, if the model is learned by the input data, have you bound the output? Not sure I understood the question, but Arif and George, do you have?
Actually, the data we take the data from the mature well field. That means we use the previous data. We use the previous data to train our model so that we can predict the future production. What will be the behavior of that reservoir in the future? We use that previous mature field data so that we can quantify at each grid block how much fluid is remaining in the reservoir, so that we can easily make a decision for the optimization section in the future.
Okay, the next question is from our colleague Abdullah, and it's regarding the sensitivity analysis. Since we used the CMG simulation modeling to generate the data, did you verify the sensitivity analysis results you get from your model with CMG built-in sensitivity analysis results?
Yes. Basically, here we use 12 input parameters for our study for studying the sensitivity analysis, and we find out that 5 parameters are the most effective parameters, and those parameters are not exactly matched with the outcome of the CMG, but it's very close to the CMG.
Yeah, I can say something here. Because of the randomness nature of this process, the values is not the same for each time you run it, but it has the same trend. Like the highest effective one is the same, but maybe a difference between 2 to 3% for each run. So the result has the same trend as CMG, but it is not the same, because even in CMG it has different because of due to each run.
So the next question is from our colleague Abdullah, and he's asking about incorporation of the relative permeability input parameters into the neural network model. Did we use static parameters such as the SW, SO, KRO, KRW, or did we just use the output of a function like Corey's function?
Okay, for our study, as I told in the fluid flow section, that we find out the saturation and relative permeability at each time. That means for 5-year period, at each time we find out at each grid locations the remaining well in the reservoir. That means the residual saturation, well saturation, gas saturation, water saturations. So we are not using exactly the static parameters. We are using the dynamic parameters with time.
The next question is from our colleague Jing Wang. What is the time step you are using with the LSTM to give the best performance of prediction?
Okay, if you are speaking about the horizon of prediction, we are produced for 1 day, and we using the history of the last 5 days. This can be used accumulative to provide a prediction for much larger period of time, but this provide us with the highest performance in LSTM.
The next question is from our colleague Adrian, is from the practical point of view, what kind of improvement in production would you expect as a result of using your model?
Now, in numerical reservoir simulator, so you have to run hundreds of runs in order to make a decision whether we have to drill some other wells or not. But if you use the machine learning techniques, so it will give you a decision-making point. That means within short span of time, we can make your decision whether we have to drill new wells, whether we have to, how you can optimize your production, at which rate you have to inject the fluid, the injection fluid. So those kind of information you can get with a short span of time using the machine learning techniques compared with the conventional simulation.
Thank you very much, everybody. I know there are more questions coming, and but it's about 10 minutes past the hour. I think we have these questions, and we will try to answer you back by email. At this point, I would like to thank our presenters for speaking today, providing the information about your project. Thank you very much. And thank you, everybody, for tuning in. Norm, if you have anything to say at the end.
Just say that all of you who typed your questions into the Q&A, that does, as I say, get put onto an Excel sheet, which I will share with our 3 presenters today. And if any of them weren't answered, they will be indicated that they weren't in that spreadsheet. And hopefully you'll get an email reply from them.
Okay. And I guess, Dan, would you like to say anything?
No, I think we've gone long enough here. This is a great topic. There's a lot of work that needs to be done here, and I look forward to see where we can apply this for other reservoirs and other applications.
Great. Thank you, everybody.
Thank you.
And as I said, this will be posted at the PTRC website, including the Q&A session, or at the PTRC YouTube site on Monday. Thanks.